Hello everyone. So in this video I'm going to talk about magnetic effects of current and magnetism. I have categorized previous year's JEE Mains questions as problem type. So I have made your life super easy. So if you follow this video till end, you have the idea about different types of questions can be asked from this chapter. If you have not watched video for other chapters, kindly do so. It can be a game changer for you at this point of time where you will get the crux of all problem types that can be asked in JEE Mains. Now let us see who will get benefited with this video. You know basics but unable to approach problems, so this video is for you. You have NCERT level knowledge but you want to crack JEE Mains problem, so this video is for you. And if you have done some formal coaching but still you want to improve your problem solving skill which is not up to the mark, so this video is for you. Right, so how you can use this video effectively? First of all, I would recommend revise the short notes which you have prepared for this chapter. Then watch this video, write down the important information in your notes. And whenever I discuss a problem, first you have to pause the video, try to solve the question on your own. If you're not able to solve the question, I'm here for you. If I talk about the weightage, so around one or two questions can be asked from this chapter. And this is the syllabus from magnetic effects of current and magnetism. So just pause the video, just have a look at the syllabus. So let us discuss this syllabus in the term of mind map. So if you talk about, this mind map does not include magnetic material. So what I'll do, I'll share the link of the video of magnetic material in the description. You can refer that video for the theory part. Okay, right. So first topic is the Biot-Savart law, and with the help of the Biot-Savart law, we'll be able to find the magnetic field produced by the current carrying conductor. So we're going to study moving charge, finite wire, semi-infinite wire, circular arc, and the magnetic field at the center of a circular coil, and the magnetic field at the at a point on the axis of the circular coil, and then the solenoid. Then there is a concept of Ampere's circuital law, and with the help of Ampere's circuital law we can find the magnetic field by some symmetrical current distribution. Like infinite wire is there, toroid is there, solenoid, then infinite hollow cylinder, infinite solid cylinder, and then we'll talk about magnetic force on a charged particle in electric field and magnetic field. So we're going to discuss two cases. So first, when the velocity of the charged particle is perpendicular to the magnetic field. So here usually we'll get a question where you have to find the radius of the circular path followed by the charged particle, time period, and the frequency. And if the velocity is not perpendicular to the magnetic field, in that case the particle follow a helical path. So what is the radius of that helical path, what is the time period, and what is the pitch? Then the Lorentz force concept, when both the electric field and magnetic field are present. Here we're going to consider two cases: electric field and magnetic field are parallel, and electric field and magnetic field are perpendicular to each other. Then the force on a current carrying conductor. So here you will study force between parallel wires and the torque experienced by a current carrying loop. Then magnets. So what is the magnetic moment and what is the magnetic field produced by a short bar magnet? Then the magnetic field suspended in external magnetic field. Then what is the time period of oscillation of the magnet? So these things we're going to cover. And as far as magnetic material is concerned, which I have already mentioned you can go to the link of that video is shared with in the description. You can watch that video and you can clear your theory part. Right, so let us start with the problem types. So the first problem can be based on the application, or you can not the application, the direct formula of Biot-Savart law. Now what is Biot-Savart law? According to this, if there is a current carrying conductor which is having a current I, and if I take a small element which is having a length dl, then we'll define a physical quantity known as current element, which is defined as I times dl. And we want to find the magnetic field at a point P, and its position vector is R. So the magnetic field at P by this current element is defined as mu naught upon 4 pi I dl cross R vector divided by R cube. Or we can write this as mu naught I dl cross R cap divided by 4 pi R square. So in the exam they can directly ask you this formula. And the direction of magnetic field will be along dl cross r vector. Along dl cross r vector. Okay, so if this current element and if this r vector lies in this plane of the in this plane only, then we can say by using right hand curl rule, if you curl your fingers from dl vector to r vector, thumb is pointing into the plane, so that will give you the direction of the magnetic field at point P. So it will be into the plane in this case. So we can find the direction by using right hand curl rule. So that direction is very important. If there is a wire which is having a current in the upward direction, then by using the same logic, the magnetic field to the right of the wire will be into the plane, and the magnetic field to the left of the wire will be out of the plane. So this is the symbol we're going to use: cross for into the plane, dot for out of the plane. If the wire is horizontal, then below this the magnetic field will be into the plane, here it will be out of the plane. If the current is going in the downward direction, then to the right it will be out of the plane, and to the left it will be into the plane. Okay, so this nomenclature you can remember. Now let's see the next concept, which is based on the magnetic field produced by a moving charged particle. So we know that when a charged particle moves, it constitutes a current. So if it is it constitutes a current, then it can also produce magnetic field. So let us see. If there is a charged particle Q and it is moving with a velocity v, and we want to find the magnetic field at point P, and the position vector of point P from the charged particle is r, and this angle is theta. Then if you look at the Biot-Savart law formula, the ideal, its unit is ampere times meter, right? So if I replace ideal with q times v, what is the unit of q times v? Q is charge, v is speed, velocity, that is meters per second. So this is again ampere meter. So what you have to do, you have to replace ideal with q times v in the Biot-Savart's formula. So you will get the magnetic field produced by a moving charged particle. So magnetic field will be given as mu naught upon 4 pi times q v cross r vector divided by r cube, or we can also write this as mu naught upon 4 pi q v cross r cap divided by r cube. Again, in this case the direction will be along v cross r, right? If we have a negatively charged particle, then the direction will be minus of v cross r, right? So the question can be based on this the application of Biot-Savart law also, right? So, and one thing I forgot to mention, mu naught is the permeability of the medium, and it will be nothing but 4 pi into 10 raised to power minus 7 in SI unit. Okay, so this you have to remember. Now the next concept is finite wire, and the magnetic field produced by the finite wire which is having current. So let us see. So there is a wire which is having a current I, and suppose we want to find the magnetic field at point P. Now what you can do, suppose this perpendicular distance is given to us, which is d. Now if I join the ends of the wire with point P, let us find this angle. So this angle is theta 1 and this angle will be theta 2. So the magnetic field will be mu naught I divided by 4 pi d, where d is the perpendicular distance of point P from the wire, times sine theta 1 plus sine theta 2, right? So this formula you can remember, or there is one more formula which you can remember for the same arrangement. If r1 is the position vector of P from the left end, from where the current is entering the wire, and r2 is the position vector of P from the right end, where the current is exiting. Now find the angle made by the current with r1 and r2. So this angle, let me call this as alpha 1 and this angle as alpha 2, right? So we can also write the same formula as mu naught I upon 4 pi d times cos alpha 1 minus cos alpha 2. But if you use this formula or this formula, you will get the same result. How to find the direction? So magnetic field at point P will be out of the plane, right? It will be out of the, you can use the same logic, right? Either you can use right hand curl rule or simply the cross product rule, right? So it comes out to be out of the plane at this particular point. Okay, right. So the next concept is the finite wire at its perpendicular bisector. So if we have a finite wire, and this is the perpendicular bisector, and we want to find the field at point P, and this wire has a current I. So this angle is theta, this angle is also theta. So in this case, theta 1 is equals to theta 2 equals to theta. So if we apply the same formula, it will be mu naught I upon 4 pi d, where d is the perpendicular distance of point P from the wire, times 2 times sine theta, or you can say it will be mu naught I upon okay, it is not visible, let me write it over here. So it will be mu naught I upon 2 pi d sine theta. So this formula you can remember. Let us see the application of that. A regular polygon of 6 sides is formed by bending a wire of length 4 pi meters. If an electric current of 4 pi root 3 ampere is flowing through the sides of the polygon, the magnetic field at the center of the polygon would be x times 10 raised to power minus 7 Tesla. The value of x is, so here we have given a regular hexagon, right? And it is having a current which is 4 pi root 3 ampere. Let us say this is the direction of the current. And we want to find the magnetic field at the center. Now if you consider any side, if I consider, let me call this as side number 1. Due to this side, the magnetic field at the center, by using right hand curl rule, it comes out to be into the plane. Similarly, if you consider the second side, due to this, the magnetic field is again into the plane. So if you take any side, the magnetic field will be into the plane. So all the fields are getting added up. So what we're going to do in such questions, first we'll find the magnetic field by one side, and then we'll multiply that magnetic field with the number of sides. So let us consider one side. Right, so if I join center with the vertices, then the distance of the center from the vertex is nothing but the length of the side of the polygon. Now what is the length? So the polygon is made with a wire of length 4 pi meters. So the length of one side, let me take side as A. So A will be 4 pi divided by number of sides. So this comes out to be 2 by 3 pi meters. So we got the length. Now what is the perpendicular distance of the center from one of the side? Now this, if you consider OAB, now this OAB triangle is a equilateral triangle, right? So we can say the perpendicular OM is nothing but root 3 by 2 times A. So let me take this as D. So D will be root 3 by 2 times A, which is 2 by 3 pi meters. So it comes out to be pi by root 3. Okay, so now it is the case of magnetic field at a perpendicular bisector. So this angle will be 30 degrees. So in this case, theta will be 30. So what is the formula? That is mu naught I upon 2 pi d times sine theta. So theta is 30 degrees, I is 4 pi root 3 ampere, and d we have just calculated, it is pi by root 3. Let us put the values. And mu naught is 4 pi into 10 raised to power minus 7. Current is 4 pi root 3, and sine 30 is 1 by 2, and 2 pi d is pi by root 3. So this will become square. Let us simplify this. So this pi square will get cancelled out. This will get cancelled out. So we get 12 into 10 raised to power minus 7 Tesla. So that is the magnetic field produced by one of the side. How many sides we have? 6 sides. So you have to multiply 12 into 10 raised to power minus 7 with 6. You will get 72. So 72 times, so x will be 72. Right? So 72 is the answer. 72 times 10 raised to power minus 7 Tesla. Again, this is the same question, but instead of a regular hexagon, we have a square. By using the same logic, we can find the answer of this question also. So I'm keeping this question as a homework for you. You can try this. The answer is 40. Now let us see the next concept, a semicircular wire. So here we have, suppose if we have given a wire which is not semicircular, suppose it subtends some angle theta at the center. So there is a wire which is having a current I, and it subtends an angle theta at the center, right? So first of all, what is the magnetic field at the center? You can curl your fingers in the direction of the current. Thumb will give you the direction of magnetic field, so it comes out to be into the plane. Since the current is clockwise, magnetic field will be into the plane, so it will be cross. And this magnetic field will be mu naught I upon 2r, r is the radius, times theta upon 2 pi. So this comes out to be mu naught I upon 4 pi r times theta. So this formula you can remember. And if you want to find the magnetic field by a semicircular wire, theta will become pi, right? So if we have a semicircular wire, theta is pi, so this comes out to be mu naught I upon 4r. And if you want to find the magnetic field via the complete loop, in that case theta will become 2 pi, and the answer comes out to be mu naught I by 2r. So let us see the question. The magnetic field at the center of a wire loop formed by two semicircular wires of radii r1 and r2. r1 is 2 pi meters, r2 is 4 pi meters, carrying current I, which is 4 ampere as shown in the figure, is alpha times 10 raised to power minus 7. So the magnetic field at O is 10 raised to power alpha times 10 raised to power minus 7 Tesla. We have to find the value of alpha, right? So what you can say, there are 4 segments, right? So we have 2 semicircles and 2 straight segments. So this one and this one, right? So let us say the current is in clockwise direction. So if you consider these straight segments, can you see this point O? If I extend these straight segment, this point O lies on that particular line. So what you have to remember, in this case, for 1 and for 2, the magnetic field will be, there will be no contribution towards magnetic field by 1 and 2 sections. So we have to consider only semicircular loop. Why? I told you the formula for finite wire, it was mu naught I upon 4 pi d times cos alpha 1 minus cos alpha 2. So here alpha 1 and alpha 2 are both 0 or 180. So that will so the field due to 1 and 2 will be 0 at O. So you don't have to consider the flat section, right? So we are left with only semicircular wire. And if you consider the bigger semicircle, again if you curl your fingers in the direction of the current, thumb is pointing into the plane. Similarly, for small semicircle, it is again clockwise, the thumb is pointing into the plane. Again we are getting into the plane, so you have to add both the fields. So we can say the magnetic field produced by the bigger semicircle will be mu naught I upon 4r2 plus mu naught I upon 4r1 due to smaller semicircle. So from this, mu naught I by 4 will be common. So 1 by r1 plus 1 by r2, which will be 2 pi and 4 pi. So let us put the values. So it will be 4 pi times current is 4 ampere divided by 4, and this will be 3 by 4 pi. So 4 pi will get cancelled out, and we have 10 raised to power minus 7 also. 4 will get cancelled out, so it will be 3 into 10 raised to power minus 7. So that should be the answer, right? Alpha will be 3. Now let us see the next concept, circular wire at its center. So magnetic field due to a circular wire at its center, and we have just discussed that if there is a circular wire which is having a current I, radius is r, you have to curl your fingers in the direction of the current, thumb will give you the direction towards you, out of the plane. So magnetic field is out of the plane and radius is r, so it will be mu naught I divided by 2r. So that you have to remember. And suppose if you want to find the magnetic field at a point on the axis, let me also show here also. So if there is a circular coil and we want to find the magnetic field at a distance x from the center of the coil, and let's say it has a current in this direction. Now if you curl your fingers in the direction of the current, thumb is pointing in the right direction. So in this case the magnetic field will be in the right direction. Let us say r is the radius, current is I, radius is r, so it will be mu naught I r square, let us say capital N is the number of turns, divided by 2 x square plus r square raised to power 3 by 2. So this formula you can remember, and this n is a natural number, right? It can't be a fraction. Got it? Right, so let us see the question. Two circular coils P and Q of 100 turns each have same radius of pi centimeter. The current in P and Q, P and R are 1 ampere and 2 ampere respectively. P and Q are placed with their plane mutually perpendicular with their centers coincide. The resultant magnetic field induction at the center of the coils is root x millitesla. We have to find the value of x, and mu naught is given as 4 pi into 10 raised to power minus 7 Tesla meter ampere inverse. Right, so let me first draw the diagram here. So we have given two perpendicular coils, right? Let us say this is x-axis, this is y-axis, and this is z-axis, and there is a red coil which lies in xy plane. Right, and let us say it has a current in this direction. So if you curl your fingers in the direction of the current, thumb is pointing in the upward direction. So we can say the magnetic field will be in this direction. This will be B1. So this is the coil P, right? Now if the coil Q is perpendicular to this. So let us say the coil Q lies in XZ plane, and they have same radius. Right? So it can be shown like this. And let us say it has a current in this direction. So if we curl our fingers in the direction of the current, thumb is pointing in the positive y direction. So that will be B2. So can you see B1 and B2 are mutually perpendicular to each other? Since they are perpendicular and we want to find the net field at the center, because their centers are coinciding now. So the field should be vector addition of these two vectors. So we can say the B net field will be root of B1 square plus B2 square. Now what is B1 here? So B1 is the magnetic field produced by the coil P. Coil P has 100 turns. So we can say 100 times mu naught times the current, which is 1 ampere, divided by 2R, and R is pi centimeter, so 10 raised to power minus 2. Right, so what is B2? So B2 will be number of turns, which is 100, times mu naught times the current, which is 2 ampere, divided by 2R, 2 times pi into 10 raised to power minus 2. Okay, so if you look at these two fields, this 100 pi 100 mu naught and the denominator, both these are common, right, in both the fields. So we can say it will be 100 mu naught divided by 2 pi into 10 raised to power minus 2 root of 1 square plus 2 square. So this comes out to be root 5. Okay, so let me further solve this. So we can say 100 times 4 pi times 10 raised to power minus 7 divided by 2 pi into 10 raised to power minus 2 times root 5. So let us simplify this. So this will give us 2. So it will be 2 into 10 raised to power, it will be 4 minus 7, so minus 3 root 5. And if you look at the question here, they have given it is root x millitesla. So we can say this is milli. So we can say it is 2 root 5 millitesla. So it means this 2 root 5 is root x. So root x is equals to 2 root 5. So x will be 4 times 5. So it comes out to be 20. So 20 is the answer of this question. Right, so I hope this concept is clear. And again, it is the same question which I'm keeping as a homework for you. You have to use the same concept, same logic, and you have to use this formula b1 square plus b2 square. So the answer of this question is option 3. Just try to solve this, you'll get this answer. The next concept is infinite wire. So if we have a infinite wire, let me show you. First, let me take a case of semi-infinite wire. So this is a semi-infinite wire. One end is not visible to us, one end is visible, right? And we want to find the magnetic field at point P. And this distance is D, let us say. So the current is in this direction. So if you again use right hand curl rule, current is coming, field will be at P, will be out of the plane. So field will be out of the plane, and the magnetic field will be given as mu naught I is the current, divided by 4 pi d. But what is a infinite wire? So let us say this is a wire, both ends are not visible to us, they are quite far from us, right? And current is in the right direction. We want to find the field at point P, which is at a perpendicular distance d. So in this case, it will be mu naught I upon 2 pi d. Okay, so this you have to remember. And the field will be out of the plane. Right, so let us see the application of this. Two long straight wires carrying equal currents in opposite direction are shown in the figure. The separation between the wire is 5 centimeter. So this distance is given as 5 centimeter. The magnitude of the magnetic field at the point P midway between the wire is dash microtesla. So we have to find the magnetic field at point P. Okay, so if you consider left wire, which is an infinite wire, the magnetic field at P will be into the plane, and due to the right wire, the magnetic field at P will be into the plane. So both the fields are getting added up. So and by symmetry, we can say both the wire will be having same magnitude of field. So let us find the field by one of the wire, and then we'll double that. So it comes out to be mu naught I upon 2 pi d times 2. So that what we have to do. So d will be 5 by 2 centimeters. So it comes out to be 4 pi into 10 raised to power minus 7. Current is 10 ampere divided by 2 pi. Okay, right. So let me eliminate this 2, right? So 2 will won't be there. D is 2 point, or we can say 5 by 2 centimeter, 10 raised to power minus 2. Okay, so this pi will get cancelled out and this will give us 2. So we got 4 times 4, that will be 16 times 10 raised to power minus 5, and we have to find answer in microtesla. So it comes out to be 160 into 10 raised to power minus 6 Tesla. So which will be 160 microtesla. So 160 is the answer of this question. Next is semi-infinite wire, which I have already discussed. The magnetic field will be mu naught I upon 4 pi d. Let us see the application of this. Right, sorry, answer is already given here. So let us calculate this. A hairpin like shape as shown in the figure is made by bending a long current carrying wire. What is the magnitude of the magnetic field at the point P, which lies on the center of the semicircle? Okay, right. So here we have 3 segments. There are 2 semi-infinite wire. Let me call this as 1. And there is another semi-infinite wire. This is 2. And there is a semicircular wire. This is 3. So we have to find field by individual segments, and then we have to vectorally add the fields. Now due to segment 1, the magnetic field at the center will be into the plane, and due to segment 2 it is again into the plane, and due to the semicircular wire it is again into the plane. By curling your fingers in the direction of the current, it is into the plane, right? So all the 3 fields are getting added up because they are pointing in the same direction. So we can say B1 is equals to B3 or B2, and it is equals to mu naught I divided by 4 pi small r, and B3 is mu naught I divided by 4r. So we have to add B1, B2 and B3. So this will become 2 times mu naught I upon 4 pi r plus mu naught I by 4R. So mu naught I by 4R will be common. And if you look at the option, everywhere they have taken R common, right? And pi also common. So let us take pi common. So let me multiply and divide with pi. So 4 pi R, and pi is also common. So this will become 2 plus pi. So pi plus 2 times mu naught I upon 4 pi R. So option 2 is the right answer. Next concept is Ampere's circuital law. So let us see what is this law. If we have given some loop, right? And there are certain current which is piercing this loop. I1 is there, I2 is there, right? This is I3. And there are certain current which are not piercing. This is I4, this is I5, right? So according to Ampere's circuital law, if we take a line integral of magnetic field on this closed loop, let us take the direction. We are taking a small element dl. So the closed integral of B dot dl will be equals to mu naught times the net current which is piercing the loop. Now, what should be the direction of the current which we have to take take positive? So if you consider I1, I1 is in the downward direction. If you curl your fingers, it is opposite to the dl vector, right? Because dl vector is going like this, right? Anti-clockwise sort of. If you look at it from the top, it is anti-clockwise, and the current I1 is going into the plane. If you look at it from the top, right? So if I point my thumb in the direction of I1, fingers are curling in the clockwise direction, but the integration is happening in the counterclockwise direction. So I1 will be negative. Similarly, I2 will be negative and I3 will be positive. So it comes out to be mu naught times minus I1 minus I2 plus I3. Okay, so if you look at this equation, the left hand side is the magnetic field produced by all the sources available, whether they are piercing the loop or not piercing the loop. So B is due to all these 5 currents, but on the right hand side we have to take only the currents which are piercing the loop. So by using Ampere's circuital law, we can find magnetic field by symmetrical current distribution, like the infinite long wire. We can find magnetic field by that, or a solid, you can say a solid infinite cylinder or hollow infinite cylinder, we can find magnetic field. Now let us see one of the application of Ampere's circuital law. In a coaxial straight cable, the central conductor and the outer conductors carry equal current in opposite directions. The magnetic field is 0. So we have to find at which place the magnetic field is 0. So here we are going to use Ampere's circuital law. Let us see. So we have given a coaxial cable. So this is the core and this is the outer conductor. Okay. At in the core, let us say the current is out of the plane, and the total current is I. And for the outer conductor, the current is into the plane, let us say. This is the cross-sectional view, right? And this current is also I. So if I consider by symmetry, if I consider an Amperian loop, right, and the center of this loop lies on the axis of the cable. Let us say the radius is R. If so, for this Amperian loop, the net current which is piercing will be 0. Why 0? If I consider counterclockwise as the direction of integration, so by symmetry, so we can say integral B dot dl. It can be written as B times 2 pi R, and the right hand side will be mu naught times. So we can say the current in the core will be positive and the current which is in the outer conductor will be negative. So it will be plus I minus I. So it comes out to be 0. So there is no net current is piercing the Amperian loop. So integral B dot dl will be 0. So B comes out to be 0. So if you consider any Amperian loop which is outside, the magnetic field will be 0. So we can say outside the cable, the magnetic field will be 0. So option 1 is the right answer. Now let us see the next concept, and it is based on the magnetic field produced by an infinite solid cylinder which is having a uniform current density. So I'm showing the cross-sectional view. So let us say there is a infinite solid cylinder and it is having the current density out of the plane. So the current is out of the plane and its radius is capital R. So the radius of the cross section is capital R, and we want to find the magnetic field inside as well as outside. So if I want to find the field, let us say at a distance R from the center. Okay, so inside magnetic field is given as mu naught by 2 J cross R. So if I want to find the field at this particular point, this will be the R vector, which is from center to that particular point, and J vector is out of the plane. So the magnetic field, if you apply J cross R, it comes out to be downward. So the magnetic field will be in this direction, right? Because J is out of the plane. Outside, if I want to find the field, let us say at a point, at this particular point, where R vector is R. So again, so here the magnetic field will be perpendicular to R vector. So outside, magnetic field will be given as mu naught times the total current, which will be J times pi capital R square, divided by 2 pi small r. Right, so this formula you can use, or you can directly write it as mu naught I upon 2 pi r. Okay, if you know the current. Right, so whatever formulas that we are discussing, you should also know how what is the graph for magnetic field with respect to the distance from the center. So that can also be asked in JEE Mains. Let us see one of the illustration based on the same concept. A long straight wire of radius A carries a steady current I. The current is uniformly distributed across its cross section. The ratio of the magnetic field at A by 2 and 2A from the axis. So here we're given a wire which is having a cross-sectional radius A. So this is A. Let us the current is out of the plane. So total current is given as I. And we want to find the magnetic field inside as well as outside. Say point A and point B, and the center is O. OA is given as A by 2 and OB is given as 2A. So this is inside and this point is outside. So we know that the formula is not same for inside and outside. So if I want to find the field inside, so magnetic field at A will be mu naught by 2 J cross R. So it will be J will be current divided by the area of cross section pi A square. So that is J. And what is R? R is OA. OA is A by 2. So this is BA, and magnetic field at B will be mu naught times I divided by 2 pi times R. R is OB. That will be 2 times A. So let us simplify this. So this will be mu naught I upon 4 pi A. This is mu naught I upon 4 pi A. So if you look at these two relations or these two magnetic field, they comes out to be same. They have same magnitude. So the answer is option 2, which is 1:1. So we have to find the ratio. Right. So let us see another illustration. A long straight wire of cross-sectional radius A is carrying a steady current I. So I'm assuming this current is uniformly distributed. The current I, and it is also given, right, uniformly distributed across this cross section. The magnetic field, so we have to find how the magnetic field is varying with respect to the distance from the center. So if you look at the formula outside, inside, magnetic field magnitude will be mu naught times J times R divided by 2. So it is directly proportional. So B is proportional to R. and outside magnetic field is mu naught I upon 2 pi r. So here B is inversely proportional to r. So if you look at the option 3, it says the directly proportional to r in the region less than a and inversely proportional to r in the region greater than a. So option 3 is the right answer. Right, so the next concept is solenoid. So in case of a ideal solenoid, the magnetic field, okay, let me just show you. Suppose there is a cylindrical core and there is a wire which we have wound over this cylindrical core. Okay, and let us say there is some current. Now the length of this solenoid is very large in comparison to the radius of the area of cross section. So when that is the case, when L is very large in comparison to R, we can say the solenoid is ideal. And in case of an ideal solenoid, the magnetic field inside the core is uniform, right? So if I show the magnetic, if you curl your fingers in the direction of the current, thumb will give you the direction of the magnetic field. So in this case, the magnetic field will be in the right direction. So in case of a ideal solenoid, somewhere in between, at the center, you can say the magnetic field at the center will be mu naught times I times n, where small n is the number of turns per unit length. Small n is the Capital N is the total number of turns in the solenoid, L is the length of the solenoid. And at the ends, so this is the end. So at the end, the magnetic field is given as mu naught I n by 2. So it will decrease. It becomes half at the end. So that you have to remember. Let us see a question. A solenoid of length 0.5 meter has a radius 1 centimeter and it is made up of m number of turns. It carries a current of 5 ampere. If the magnitude of the magnetic field inside the solenoid is 6.28 into 10 raised per minus 3 Tesla, then the value of m. So we have given magnetic field and we know the formula. It will be mu naught I n. So here it will be mu naught I n is nothing but small m divided by the length, and length is given as 0.5, right? So let us put the values. We have to find the value of m. So m will be BL divided by mu naught times I. So B is 6.28 is nothing but 2 pi. So 2 pi into 10 raised per minus 3 is the magnetic field. Length is 0.5. Mu naught is 4 pi into 10 raised per minus 7. And the current is 5 ampere. So let us simplify this. So this will give us 2 and 2 and 5 will be 10. So it comes out to be 5 into 10 raised per minus 4 plus 7 minus 1. So it will be 500. So 500 is the answer. Okay. Now here we have done similar cases, right? So we have given 4 different arrangements and we have to find the magnetic field at O. So I'm keeping this as a homework. You can try this and check whether you're getting 3 as the answer or not, right? So 3 is the answer of this question. So do practice based on the concept that we have discussed so far. Now let us see another question. So in this question, it based on the graph, right? Whatever we have studied based on those formulas in the form of graph. So again, I'm keeping this as a homework. So try to do this question because you know all the formulas and you can find this. Now one thing is there, like if you look at the A part in list 1, it is the magnetic susceptibility and the magnetizing field. So this thing you can remember. Magnetic susceptibility is the property of the material, so it does not depends upon the magnetizing field. So the graph will be there will be no change in the magnetic susceptibility, so it will be constant, right? So this you can remember. The remaining things you can do on your own very easily because you know all the relations of magnetic field for different arrangement. Okay, so the answer will be 4 for this particular problem. Now let us see the next concept, and it is based on the magnetic force on charge. So if there is a charged particle which is moving, let's say there is a positive charged particle and it has a velocity v, and the magnetic field say is in this direction, and the angle between magnetic field and the velocity is theta, then the force experienced by the charged particle will be q v cross b, and the direction will be along v cross b for positively charged particle, and it will be minus v cross b for negatively charged particle. And if there is a charged particle which is placed in electric field, there is some external electric field, then the electric force will be q times e. Now the electric force is along the electric field in case of a positive charged particle, and it will be opposite to the electric field in case of a negatively charged particle. So do remember this. So but the force is perpendicular to both the velocity vector and the magnetic field. So we can say force lies perpendicular to the plane containing the velocity and the magnetic field. Since force is perpendicular to velocity, work done by the magnetic field will always be zero. So there will be no change in the kinetic energy produced by the magnetic field. So that thing you should keep in your mind. Let us see the question based on this formula. A charge of 4 microcoulomb is moving with a velocity 4 into 10 raised per 6 meters per second. So velocity is given, charge is given along the positive y-axis, and velocity is in positive y-axis. Let me call this as j cap, under the magnetic field which is 2k cap. So magnetic field is in z direction. The force acting on the charge is x I cap Newton, the value of x. So we have to use F is equals to q v cross b. So let us put the values. Q is 4 into 10 raised per minus 6, and v is 4 into 10 raised per 6 j cap, cross with magnetic field which is 2 k cap. Now we can take all the constant factors outright. Let us consider all these factors together. So this will be 16 times 2 times 10 raised per 0, and we have j cross k. So j cross k is I, so this will be 32 times I cap Newton, right? So x will be 32. So 32 is the answer. Let us see another question. An electron moves through a uniform magnetic field B, which is B naught I cap plus 2 B naught J cap Tesla. At a particular instant of time, the velocity of the electron is 3 I cap plus 5 J cap. If the magnetic force acting on the electron is 5 E K cap, where E is the charge on the electron, then the value of B naught is, again, the direct application of the same formula. So F will be Q V cross B. So let us put the values. So it is an electron, so I'm taking E, which is negative, right? And V is 3 I cap plus 5 J cap. It's a cross product with magnetic field, which is B naught common I cap plus 2 J cap. So let us simplify this. It will be E times B naught. Then we have 3 I cap plus 5 J cap cross with I plus 2 J cap. Okay, now we can distribute over addition, right? So 3I cross with I plus 2J, and then 5J cross with I plus 2J. So when cross product of 3I cap and I cap will be 0, and the cross product of 3I cap and 2J cap will be 6K cap. So it will be 6K cap, and then the cross product of 5J cap with I cap will be minus K cap. So this will be minus 6K cap, and the cross product of 5J cap with 2J cap will be 0. So E B naught. So this comes out to be E B naught. It will be, sorry, it should be 5, not 6. K cap. Now this thing is given as 5 times E K cap. So if we compare B naught comes out to be 5 Tesla. So 5 is the answer. Okay, let us see another question. an electron is projected with a uniform velocity along the axis inside a current carrying long solenoid, and then we have to see like what happens to the motion of the electron. So if this is the core of the solenoid, we know that the magnetic field is along the axis, right? Depending upon the direction of the current, it will be along the axis. Suppose the electron is moving in this direction, which with certain velocity. Now, since the velocity is parallel to magnetic field, it will not experience any magnetic force, so there will be no change in the velocity. So we can say the electron will continue to move with uniform velocity along the axis of the solenoid. So option 1 is the right answer. Now the next concept is based on like when the velocity of the charged particle is perpendicular to the magnetic field. So when magnetic field, let us say, is into the plane, and there is a charged particle which is having a velocity, say v, in this direction. So it will experience a force which is perpendicular to velocity vector as well as the magnetic field. So the force will be in the upward direction, and this force will be having a constant magnitude. So this F will be QVB, and due to this force the charged particle will move in a circular path, and the radius of this circular path is given as mv upon qb, or we can write this as p upon qb, where p is the linear momentum. P can also be written as root of 2mk by qb, where k is the kinetic energy. And if we are accelerating a charged particle from rest with a potential difference v, then k can be written as q times v, so that will be root of 2mqv divided by qb. So that is the radius, and the time period of one orbit will be 2 pi m upon qb, and the frequency, so the number of um, oscillations or number of revolutions per second will be qb by 2 pi m. And if you want to find the angular frequency, omega will be 2 pi f, so that will be qb by m. So these formulas you have to remember, and you should also know what are the charges and the masses of important charged particles. For example, electron. Let me quickly write here. So we have mass and charge, and here we have the particle electron. So in case of electron, mass is mass of the electron. Mass of the electron is 9.11 into 10 raised per minus 31 kilograms. And the charge will be minus E. And for proton, mass is mp. Mass of the proton is 1.67 into 10 raised per minus 27 kilograms, and the charge is plus E. And for deuterium or deuteron, which is the isotope of hydrogen, deuteron, so mass will be 2 times the mass of proton, and the charge will be E. And for tritium, mass will be 3 times mass of proton, and the charge will be E. And for alpha particle, mass is 4 times the mass of proton, and the charge will be 2 times E. And neutron, the charge on the neutron will be 0, and the mass of the neutron will be nearly same as the mass of the proton. So neutron, okay, let me write it over here. So a neutron mass is nearly equals to mass of the proton, and the charge will be 0, right? So if you pass neutron in magnetic field, it will not experience any magnetic force because it is neutral. So this you should remember. Now let us see a question based on these formulas. Two particles x and y having equal charges are being accelerated through the potential difference v, same potential difference. So they have same charge, same potential. Therefore, after enter normally in the region of uniform magnetic field and describe circular path of radii r1 and r2 respectively, the mass ratio of x and y is, so we have to find mx upon my. So what we're going to do, let us write down the formula of radius. So radius is root of 2mqv divided by qb. Right, so now let us see the constant parameters for both the charged particle. So they have same charge, so let me highlight that. So they have same charge, magnetic field is same, potential is same, so we can say m is directly proportional to square of the radius. So we can say mx upon my will be r1 by r2 square. So option 2 is the right answer. So whenever you get such kind of a question where you have to compare, always use proportionality. It will make your job easy, right? So let us see next problem based on the same concept. A proton and a deuteron having same kinetic energy enters the region of uniform magnetic field moving perpendicular to B. The ratio of the radius of deuteron to the radius of proton. Let me again write down the formula, and here they have given same kinetic energy, so I'm going to use root of 2 mk divided by qb. Now we have to highlight the terms which are constant for both. Magnetic field is same and they have same kinetic energy, and one is proton, other is deuteron, so their charges will be same, right? Charge is same but their masses will be different. So from this we can say radius is directly proportional to square root of mass. So we can say radius of deuteron to radius of proton will be root of 2 mp upon mp, so that will be root 2 by 1. So option 1 is the right answer. Now the next concept is when velocity is not perpendicular to the magnetic field. Let me just show you the situation. Suppose there is a positively charged particle and its velocity is v and it makes an angle theta with magnetic field. So in this case, when velocity is not perpendicular, the particle will follow a helical path. So the particle has two components. One will be along the magnetic field, the velocity component, that will be v parallel. So v parallel is v cos theta, and there is another component which is v perpendicular, and v perpendicular is v sin theta. Now this v perpendicular is responsible for rotating this particle in a circular path in a plane which is perpendicular to the magnetic field. But v cos theta is the component which drift the charged particle in the direction of magnetic field. So v perpendicular try to move this charged particle in a circular path, but because of v parallel, this charged particle will drift in the direction of magnetic field. So here we can say it will follow a helical path, and after one revolution it will pass through the point which lies on the magnetic field line, right, on this B line. Okay, so here what you have to remember, you should remember what is the radius of this helical path. So radius is mv perpendicular divided by qb, and the time period is 2 pi m by qb, and there is a term pitch. Pitch is the displacement along magnetic field in one revolution. So this is the pitch, right? So pitch will be time period multiplied with the velocity in the along the magnetic field v parallel. So that will be 2 pi m upon qb times v parallel. So these formulas you have to remember, right? So let us see the question based on the same concept. A charged particle moving in magnetic field B has the component of velocity along a magnetic field as well as perpendicular. The path of the charged particle will be, yeah, we have just discussed this. It will be a helical path with the axis along the magnetic field, right? And if you look at the option 1, helical path with its axis perpendicular, that is incorrect. If you look at this diagram, the axis is in the right direction only, right? So that is the axis of the helical path, and which is in the direction of magnetic field. So option 3 is the right answer. Option 2 says straight along the direction of the magnetic field. That is incorrect. it is not the same, axis is not coinciding with the magnetic field. Straight along the direction of magnetic field, no. So circular, that is wrong. So option 3 is the right answer. That is the next question. A particle of mass m in charge q has a initial velocity which is v naught j cap. This is j cap, right? And if the electric field is E naught I cap and magnetic field is B naught I cap acts on the particle, its speed will double after the time. Okay, so let me just show you a situation what we have given. So there is a charged particle which is having a charge q, mass is m, and its velocity is in y direction, which is v naught, and the electric field and magnetic field both are in the x direction. So this is given as E naught, this is B naught. Now if you look at E naught, this E naught will try to accelerate the charged particle in the direction of electric field. Now due to this, we can say there will be a velocity component in the direction of electric field, but this magnetic field will not change the speed of the charged particle, which is perpendicular to the plane of the in a plane which is perpendicular to magnetic field. So we can say at any given instant the velocity in a plane which is perpendicular to magnetic field will remain, which its magnitude will still remain v naught, but the velocity component which is along the electric field will be given as, by kinematics, it will be the acceleration. So we can use v equals u plus at and 0 in the x direction, and the acceleration will be q times E naught divided by m times t. So we can say velocity at any given time, speed at any given time, will be root of v naught square plus q E naught by m t square. And we want to find the time when this speed will become double. So put this speed equals to 2 times v naught, because initial speed was v naught. Now let us square this. So when we square this, it comes out to be q E naught by m t whole square equals to 3 v naught square. Now from this, t comes out to be root 3 m v naught divided by q E naught. So option C is the right answer. Now let us see the next concept, and it is based on Lorentz force. And what is the Lorentz force? When both electric field and magnetic field are present in space, then there will be electric force as well as magnetic force. So the Lorentz force can be written as q times E plus q v cross b, right? Let us see the question. The electrostatic force and magnetic force, so F1 is the electrostatic force, F2 is the magnetic force, acts on the charged particle q moving with velocity v, can be written as q times E and q v cross b. So option 1 is the right answer, direct application of the formula. Let us see the next case. A proton moving with a constant velocity passes through a region of space without any change in its velocity. Okay, so the velocity of the charged particle is not changing. If electric field and the magnetic field represents the like E and B represent the electric field and the magnetic field, then the region of space may have. So we have to check these 4 options. So option A states that electric field is 0 and magnetic field is 0. If electric field and magnetic field both are 0, then Lorentz force will be 0. If there is no force acting on the charged particle, its velocity will not change as per Newton's first law. So this option this A is possible, right? So let's B is electric field is 0 but magnetic field is non-zero. So if electric field is 0, there will be no electric force. If magnetic field is non-zero, but if velocity and magnetic field are parallel or anti-parallel, if we have these two arrangements, then magnetic force is also 0. So if magnetic force is 0, electric force is 0, then option this B is also possible. Electric field is non-zero, magnetic field is 0. If magnetic field is 0, there will be no magnetic force, but electric field is non-zero, there will be electric force, and electric force is will never be 0 in this case. So the particle will accelerate, so its velocity will change. So C is incorrect. Let us say D, electric field is non-zero, magnetic field is non-zero. Right. So if electric field and magnetic field are mutually perpendicular, let us see a situation. Suppose electric field is in the downward direction and there is a charged particle which is going, positively charged particle which is going in the right direction with velocity v. And let us say the magnetic field is into the plane. So if you look at the forces, there will be an electric force which is in the downward direction, and there will be a magnetic force which is in the upward direction. If FB is equals to FE, right? If these two forces are equal, then we can say QVB should be equals to QE. If velocity, if the speed of the charged particle is E by B, then we can say the charged particle will cross this field, this combination of field, undeflected without any change in its velocity. So D is also correct. And this arrangement, so this arrangement is known as velocity selector, right? So choose the most appropriate answer from the option. So A, B, D. So A, B, D. So option 3 is the right answer. Let us see another question. An electron with kinetic energy 5 electron volt enters a region of uniform magnetic field of 3 microtesla. So kinetic energy is given and magnetic field is given and perpendicular to its direction. An electric field E is applied perpendicular to the direction of the velocity and the magnetic field. The value of E so that the electron moves along the same path. So the electron moves along the same path. It is the same case of velocity selector. V has to be E by B, which we have just discussed, right? Or we have to, and here we have to find the electric field. So electric field magnitude will be V times B. And kinetic energy is given, so we can say kinetic energy is 5 times electron volt, which is 1.6 into 10 raised to power minus 19 joules, and this can be written as half mass of the electron, which is 9 into 10 raised to power minus 31 given in the question, times v square, so 5 times 1.6 into 10 raised to power minus 19. So let us simplify this. So it will be v square will be 16 by 9 into 10 raised to power 12. So this will be 4 by 3 into 10 raised to power 6 meters per second. So we got V. So put the value 4 by 3 into 10 raised to power 6. Magnetic field is given as 3 micro Tesla, 10 raised to power minus 6. So it will be 4 volt or Newton per coulomb, right? So 4 is the answer of this question. Right, so let us see one more question. Given below are two statements. Statement 1, the electric force changes the speed of the charged particle and hence changes its kinetic energy. So that is fine, electric force do work, due to which the kinetic energy of the charged particle will change. Whereas the magnetic force does not change the kinetic energy of the charged particle because the magnetic force is always perpendicular to the velocity. So the work done will be zero. Since there is no work done by the magnetic field, there will be no change in the kinetic energy. So statement 1 is fine. Let us see the statement 2. The electric force accelerates the positively charged particle perpendicular to the direction of the electric field. That is incorrect. We know that acceleration is in the direction of electric field for the positively charged particle. So option 2 is incorrect. So statement 1 is correct, statement 2 is incorrect. So option C is the right answer. Now the next problem type of the concept is magnetic force on a current carrying conductor. So let us see. So if I have a conductor which is having a length, let us say dl, and it is having a current I, and it is placed in a magnetic field B, then the force is given as I dl cross B. Now suppose if I have an irregular wire AB and it is having a current I and it is placed in uniform magnetic field B, then the magnetic force experienced by this irregular wire will be I times L cross B, where L vector is a you can say the shortest vector from A to B. and its direction will be in the direction of L cross B. So that you should remember. And but if we have a closed loop, suppose there is a closed loop which is placed in uniform magnetic field and it is having some current I. In this case, this L vector will be 0. It's a null vector, so the force will be 0. Okay, so these concepts you have to remember. Now let us see, not this one, this question. A rigid wire consists of a semicircular portion of radius r and two straight sections. The wire is partially immersed in a perpendicular magnetic field B, which is B naught J cap. The magnetic force on the wire, if it is having a current I. Okay, right. So let us see what we can do in this case. So there is a current which is entering from point P and it is leaving from point Q. So what you can do, you can say we have a regular wire. So and it is placed in a uniform magnetic field. So we can draw, we can join the ends with the shortest vector. So that will be the L vector. Now if you look at this portion, this is a semicircle, right? So this L vector magnitude is nothing but 2r. Right, so the wire is partially immersed in a perpendicular magnetic field, which is actually, this is not J cap, it is K cap, right? This is K cap. So L vector is in the x direction, so L vector is 2r I cap. Magnetic field B is in z direction, which is B naught K cap. So the force will be I L cross B. So IL in this case is 2r I cap cross with B naught K cap. So this comes out to be minus 2r I times B naught. And the direction will be minus J cap. So option 4 is the right answer. Right, so let us see the next question. The magnetic field existing in a region is given by 0.2 times 1 plus 2x K cap Tesla, a square loop of edge 50 centimeter carrying 0.5 ampere current. So we have given side, let us say this is A and this is the current I, is placed in xy plane with its edge parallel to x and y axis as shown in the figure. The magnitude of the net force experienced by the loop. So we have to find the net force, and if you look at the magnetic field, it is in the z direction, but its value depends upon x. So what we can say, if I consider any particle, any element on the left side of the square loop, the magnetic field will be having a constant magnitude. Similarly, if I consider any point on the right side of the square loop, the magnetic field will be having a constant magnitude. Right, so in this such kind of a question, you have to break down the problem. So we're going to find the forces on all the sides, and then we'll take the vector addition and we'll get the answer. Let us see. So let me name it. So say this is P, this vertex is Q, this is R, and this is S. So first I'm finding the force experienced by SP. This is the side SP. Now what is the magnetic field at SP? Let me call this as B1, and what is the X value? It is given as 2 meters. So magnetic field will be 0.2 times 1 plus 2 times 2, which comes out to be 1 Tesla. And its direction is in the positive z direction, so it will be out of the plane. So magnetic field is out of the plane. Current is in the downward direction, and current is 0.5 ampere. So if I apply I L cross B, L is in the downward direction, B is out of the plane. If you apply L cross B, it comes out to be towards left. So the magnetic field is in the left direction. Sorry, so magnetic force is in the left direction. Let me name it as F1. So F1 magnitude will be I L or B1, and L is nothing but A, so it will be 0.5 times 0.5 because it is 50 centimeter and 1 Tesla. So this will be 1 by 4 Newton in the left direction. If you do the same working for RQ or QR, let us say the magnetic field is B2 at the location of QR. So magnetic field will be 0.2 times 1 plus, since the edge is 0.5 meters, so the x coordinate will be 2.5 meter. So it will be 2 times 2.5. So 2.5 times 2 will be 5, 6. So this will be 1.2 Tesla. So let me call this force as F2. And what is the direction? L is in the upward direction, B is out of the plane. If you curl your fingers, thumb is pointing in the right direction. So force will be in the right direction. So F2 magnitude will be ILB. So I is 0.5, length is 0.5, B is 1.2, right? So this comes out to be 1 by, or you can say 0.3, 0.3 Newton. And we have to find the magnitude of the net force experienced by the loop. Okay, now if you look at both RS and PQ, so here we have RS and this is PQ, and if I consider same elements, element at the same location, right, at same value of x, so this element which is having a current in the left direction will experience force in the upward direction. Let me call this force a dF. Whereas this element which is having a current in the right direction will experience force in the downward direction. So these two forces are equal and opposite, so they will cancel out each other. So we can do the same working for all the symmetrical elements. So we can say the force SR plus force PQ should be 0, right? So this vector addition of the net force acting on SR and PQ will be 0. So if I want to find the net force, so the net force magnitude will be nothing but it will be F2 minus F1, right? Can you see? F2 is having a greater magnitude. It is 0.25 Newton and it is 0.3. So the difference will be 0.3 minus 0.25. So it comes out to be 0.05. And we have to find in milli-Newton. So this 0.05 can be written as 50 milli-Newton, right? 0.05 Newton is 50 milli-Newton. So 50 is the answer, right? So I hope this concept is clear. Now let us see one more question. A 2 ampere current carrying a straight metal wire of resistance 1 ohms. Resistivity is 2 into 10 raised by minus 6 ohms meter. Area of cross section is given. Mass is also given. Is suspended horizontally in midair by applying a uniform magnetic field B. The magnitude of B. Okay. Let us say there is a wire which is having some current. Its resistance is given, resistivity is given, right? Current is also given. Area of cross section is given, mass is given. So what we can say, since it is suspended in mid-air, so the net force on this wire must be 0. So there will be a gravitational force in the downward direction. Mass is also given, so it will be 0.5 times G, and G is given as 10. So weight is in the downward direction. There has to be a magnetic force in the upward direction. Only then this wire can suspend in mid-air. So this force will be what? It will be I L B, right? So the current is given, length is not given in the question, so we can find the length since resistance is given. Resistance is rho L by A. Now from this we can find the length. So length will be resistance times the area of cross section, which is 10 into 10 raised per minus 6 divided by the resistivity, which is 2 into 10 raised per minus 6. So this comes out to be 5 meters. So length is 5 meters, magnetic field is, we have to calculate, current is 2 ampere. So we can say 2 times 5 times B is equals to 5 Newton. So B will be 1 by 2 Tesla, or this can be written as 0.5 Tesla or 5 into 10 raised per minus 1 Tesla. So the answer will be 5. So we have to find this, right? Okay, let us see another question. A square loop of edge 2 meter carrying a current of 2 ampere is placed with its edges parallel to x and y axis. A magnetic field is passing through the xy plane and expressed as b naught times 1 plus 4x k cap, where b naught is 5, the net magnetic force. It is again same question which we have just discussed. Let me show you the question. It is based on the same concept, right? So I'm keeping this question as a homework. Kindly try to do this question. The answer will be 160 Newton, right? So try to do this. Right, so let us see the next question. A horizontal component of Earth's magnetic field at a place is 3.5 into 10 raised to power minus 5 Tesla. A very long straight conductor carrying current root 2 ampere in the direction from south to east to northwest is placed. The force per unit length experienced by the conductor is. Okay, let us first draw the diagram. So this is north, this is south, east, and west. And the horizontal component of Earth's magnetic field is from south to north. So this is the direction of BH. BH is the horizontal component of Earth's magnetic field. And there is a conductor which is having current in the direction from south southeast. So the current is from southeast to northwest. In this direction, right? That is the current root 2 ampere. The force per unit length experienced by the conductor. So we can say force will be what? Force will be IL cross B. Right? Now the magnitude will be what? Its magnitude will be ILB sine theta, where theta is the angle between the current and the magnetic field. So this angle is 45 degree. So current is root 2, length is not given, magnetic field is 3 into 10 raised to power minus 5, and sine 45 is 1 by root 2. So this root 2 will get cancelled out. So we have to find force per unit length. So force per unit length will be 3 into 10 raised to power minus 5. So this is not 3, this is 3.5. Okay, so and we have to find the force per unit length. So this will be 35 times 10 raised to power minus 6 Newton per meter. So answer will be 35. Right, so 35 is the answer. Let us see another question. A triangular shaped wire carrying a current 10 ampere is placed in a uniform magnetic field of 0.5 Tesla is shown in the figure. The magnetic force on the segment CD. So we have to find the magnetic force on segment CD, which is having a length 5 centimeter, and the current is 10 ampere, and magnetic field is in the right direction, which is given as 0.5 Tesla. Now what is the direction between the L vector and the magnetic field? It is same as the angle between the current and the magnetic field, and this angle comes out to be what? Let us see. BCD is a equilateral triangle, so this angle will be 60 degrees. So this is also 60, right? So we can say IL cross B will be ILB sine 60 degree. Current is 10, length is 5 centimeters, so 5 by 100. Magnetic field is 0.5 Tesla, and sine 60 is root 3 by 2. Right, so this comes out to be, this 10 will get cancelled out, so we have 25 1 by 2, so 5 by 4 times root 3 times 10 raised to power minus 1. Okay, let us simplify this. So we have 1.25 times 1.73 times 0.1. So it comes out to be nearly 0.216. So option C is the right answer. So now let us see the next question. As shown in the figure, a metallic rod of linear density 0.45 kilogram per meter is lying horizontally on a smooth inclined plane which makes an angle of 45 degree with the horizontal. The minimum current flowing in the rod required to keep it stationary when 0.15 Tesla magnetic field is acting on it in a vertically upward direction. Right, so friction is not there, so we have smooth surface. So it means we have to find the magnetic force which must be balancing the weight component. So let us see. Let us first draw the diagram. This is the inclined plane. And this angle is given as 45 degrees. And there is a rod which is having a current. Right, so there will be a weight component down the incline, right? And the magnetic field is in the upward direction. So B is in the upward direction. So due to this magnetic field, let us say the current is, and it is given, right, current in this direction. So current will be like this, and this current we have to find, right? We have to find this current I. Now the current is in this particular direction, the force will be in the horizontal direction. So let me show the direction of the force. So if I apply I L cross B, it will be in horizontal direction. Now this force will be having two components. So that will be I L B. Now its component which is along the inclined plane will be I L B cos 45 degree. So we can say the weight component which is mg sine 45 degree should balance this component which is ILB cos 45 degree. So we can say mg sine 45 should be equals to ILB cos 45. Right, so from this I will be mg tan 45 divided by LB. Mass per unit length is given. So m by L will be 0.45. G we have to take 10. Tan 45 is 1. B is 0.15. So this comes out to be 3. So it should be 30 ampere. So the minimum current which is required to keep this conductor stationary is 30 amperes. So option A is the right answer. Now let us see the next problem type, and it is based on the force between two parallel currents or anti-parallel currents. So if we have given, say, two parallel currents, it is having a current I1 in the upward direction, and there is another infinite wire which is having a current I2 in the upward direction. So if we want to find the force experienced by L length of wire 2 due to the magnetic field produced by the current I1 will be, so force per unit length will be mu naught I1 I2 upon 2 pi d, where d is the perpendicular distance between the two parallel wires. If they have current in the same direction, we call them parallel current, and in this case the force will be attractive. So there will be a force in left direction. But if we have anti-parallel current, then the force will be repulsive. Now let us see the question based on the same concept. So we have given a wire X of length 50 centimeter carrying a current of 2 ampere is placed parallel to a long wire Y of length 5 meter. So this wire Y length is 5 meter, whereas the wire X is having a length 0.5 meters, right? So the wire Y carries a current of 3 ampere, and the distance between the two wire is 5 centimeter, and the current flows in the same direction. The force acting on the wire Y is, so we want to find the force experienced by wire Y due to the wire X, right? But wire Y is quite large, quite long as compared to wire X. Okay, so what would be the easiest approach would be, so we can find the magnetic field produced by the wire Y at the location of X, and then we can find the force experienced by wire X per unit length. Then we can find the force experienced by the entire length of the wire X, that will give us force on wire X due to wire Y. And then we can use Newton's third law, which says every action has an equal and opposite reaction. So once we know the force experienced by wire X, we can find the force experienced by wire Y, which will be just opposite to the force experienced by wire X. So let us do that. So if I consider, say, L length of wire X, then the force experienced by this length will be magnetic field produced by the wire Y at the location of this length, which will be mu naught times 3 divided by 2 pi d. D will be 5 into 10 raised to power minus 2 times, so that will be the magnetic field times the length times the current, that will be 2. So that is the force for length L. So force per unit length we got. It will be mu naught times 6 divided by 10 pi into 10 raised to power minus 2. So what is the force experienced by wire X? So we can say it will be mu naught times 6 divided by 10 raised to power minus 1 times pi times the length of the wire X, which will be 0.5. So this can be written as 4 pi into 10 raised to power minus 7 times 3 divided by 10 raised to power minus 1 times pi. So this comes out to be 1.2 into 10 raised to power minus 5 Newton. So we can say this is the force experienced by this entire wire X due to wire Y. So we can say then wire Y will also experience the same attractive force in the left direction, that will be 1.2 into 10 raised to power minus 5 Newton. So if you look at the option A is the right answer. Now let us see the next concept, and it is based on the magnetic dipole moment. So let us see what do we mean by magnetic dipole moment. So if there is a current carrying loop which is having a current I, and the area of this loop is A, then we can say this current carrying loop will behave like a magnet, and the magnetic dipole moment of this magnet will be in this particular direction, and you will get this direction by curling your fingers in the direction of the current. Thumb will give you a direction of magnetic dipole moment. So I'm denoting this with capital M. So its magnitude will be NIA, where N is the number of turns, I is the current, and A is the area bounded by one of the coil. So we can use this, but suppose if there is a charged particle which is moving in a circular path, in this case the current constituted by this moving charged particle will be Q times the frequency. And how to find the frequency? Let us say V is the speed. So frequency, or you can write this as Q by the time period. So it will be Q divided by 2 pi R, where R is the radius of this circular path, times V. So that is the current. So if you want to find the magnetic dipole moment of a moving charged particle in a circular path, it will be I times the area of this loop, that will be pi R square. So it will be QV divided by 2 pi R times pi R square. So pi will get cancelled, R will get cancelled. So this comes out to be QVR by 2. Or if I multiply and divide with mass, MVR is the angular momentum of this moving charged particle in a circular path. So we can say the ratio of the magnetic dipole moment and the angular momentum is Q by 2m. But if we have a negatively charged particle, then the magnetic dipole moment and the angular momentum will be in the opposite direction. So there will be a negative sign. So let us see the question based on this concept. The magnetic moment of an electron E revolving in an orbit around the nucleus with an orbital angular momentum is given by. So we know that. So here they have taken mu L for angular momentum and L for mu L for magnetic moment and L for angular momentum. So mu L should be equals to negative of Q by 2m times linear momentum, right? So that should be the answer. So option B is the right answer. Now the next concept is based on the torque experienced by a current carrying loop in external magnetic field. So here the torque will be magnetic dipole moment cross with magnetic field, so M cross B. So let us see a question. A uniform magnetic field of 2 into 10 raised to power minus 3 Tesla is along the positive y direction, and the rectangular loop of side 20 by 10 centimeter with a current of 5 ampere is in YZ plane. Okay, let me first draw the diagram. Let us say this is y-axis, this is z-axis, and this is x-axis. Now there is a loop which lies in YZ plane, right? So this is the loop, and its dimensions are also given. So let us say this side is 20 centimeter and this side is 10 centimeter. And the current is 5 ampere in YZ plane. The current is in the anti-clockwise sense with reference to the negative x-axis. So if you look at this loop from the bottom, the current is anti-clockwise, so we can say it will be in this direction. So we can say the magnetic dipole moment of this current carrying loop will be in the positive x direction. So the current is 5 ampere. So what is the magnitude and the direction of the torque? So we want to find the torque, and we have given magnetic field is in positive y direction. So magnetic dipole moment is in positive x and magnetic field is in positive y direction. So this is the direction of magnetic field. So M cross B comes out to be positive z. So if you look at the option, it should be in the positive z direction. So the only option is option 1, which is giving positive z direction. So there is no need to calculate the magnitude also. So option 1 is the right answer. If you want to find the magnitude, it will be MB sine 90 degree, where magnetic dipole moment will be current times the area of this loop, length times breadth, times magnetic field. Sine 90 is 1. So current is 5 ampere, length is 0.2, breadth is 0.1, magnetic field is 2 into 10 raised to power minus 3. So this comes out to be 2 into 10 raised to power minus 4 Newton meter. Got it? So option 1 is the right answer. Now the next concept is based on the potential energy associated with a current carrying loop placed in an external magnetic field. So if we have given a current carrying loop, then the potential energy is defined as minus m dot b, or you can write this as minus mb cos theta. Now if the magnetic dipole moment and the magnetic field are in the same direction, then we can say they are this configuration is stable configuration, and in stable configuration potential energy is minimum and it will comes out to be minus mb. But if they are in opposite direction, m is in the left direction, b is in the right direction, then this is a unstable configuration. Here the potential energy will be maximum because the angle is 180 degrees. So cos 180 will be negative 1, so that will be plus mb. And if we want to find the work that external agent has to do from one orientation to the another orientation, so we can write this as u final minus u initial, where u final will be minus mb cos theta 2 minus of minus mb cos theta 1. So you can remember it will be mb cos theta 1 minus cos theta 2. So that is the work done by the external agent in rotating the magnetic dipole moment in external magnetic field. And theta is the angle between magnetic dipole moment and the magnetic field. So let us see a question. A circular coil having 200 turns and 2.5 into 10 raised to power minus 4 square meter area. So we have given area, number of turns is given, and it is carrying a 100 microampere current. Current is also given. Is placed in a uniform magnetic field of 1 Tesla. Magnetic field is also given. Initially, the magnetic dipole moment was directed along B. So initially, magnetic dipole moment was pointing in the direction of external magnetic field. Amount of work required to rotate the coil through 90 degree from its initial orientation such that magnetic dipole moment becomes perpendicular to B. So we can say theta 1 in this case is 0. Now we are rotating the magnetic dipole moment by 90 degree. Now the angle between magnetic dipole moment and B will become 90 degree. So what is the formula? So work done by the external agent will be mb cos theta 1 minus cos theta 2. So so what is m? So magnitude of n will be nia. So n is 200. Current is 100 into 10 raised to power minus 6 ampere, and the area is 2.5 into 10 raised to power minus 4. So if we simplify this, so 2.5 times 2 will be 5, so this will be 500 times 10 raised to power 0, so that will be 500, right, in SI units. So 500 times the magnetic field, which is 1 Tesla, times cos 0 degree minus cos 90. Cos 90 is 0, cos 0 is 1, so that comes out to be 500. Okay, let me just check one more time. Right, so this will be 200. So that will get, oh sorry, so this should be not 0, so it will be 10 raised to power minus 8, sorry, it should be minus 8. So 500 into 10 raised to power minus 8, 10 raised to power minus 8, so it will be 10 raised to power minus 8, so it will be 5 microjoules. So 5 is the answer. I hope this concept is clear. So again, this is based on the same concept. I am keeping this as a homework for you. Again, the same formula you have to use. Right, let us see this question. The magnetic moment of a bar magnet is 0.5 ampere meter square. It is suspended in the uniform magnetic field of 8 into 10 raised to power minus 2 Tesla. So magnetic field is given, magnetic dipole moment is given. The work done in rotating it from its most stable to most unstable position. So we know that in potential energy in stable position is minus mb, and potential energy in unstable position or configuration is plus mb. And so what is the work done by the external agent? That will be from most stable to unstable. So mb minus of minus mb, so this comes out to be 2 times mb. So 2 times 0.5 times 8 times 10 raised to power minus 2. So it is 8 into 10 raised to power minus 2 joules. So option 1 is the right answer. Now the next concept is based on moving coil galvanometer. So in case of a moving coil galvanometer, deflection per unit current is given as NAB divided by C, where N is the number of turns of in the galvanometer, and A is the area of one of the coil, and B is the magnetic field, and C is the torsional constant of the spring. Theta is the deflection produced in the galvanometer, and I is the current. Now this is also known as current sensitivity. Current sensitivity. And if I divide both sides with the resistance of the galvanometer, we'll get voltage sensitivity. So NAB divided by C times R. So this will be voltage sensitivity. So when the galvanometer needle is stable, then we can see the torque of the spring should be equals to torque produced by the magnetic field. So this will be C times theta, and this will be NIAB, right? So from this we got these two results. Now let us see the question. The current sensitivity of a moving coil galvanometer is increased by 25%. This increase is achieved only by changing the number of turns of the coil and the area of cross section. So what is current sensitivity? It is theta by I, which is NAB divided by C. And we are changing the number of turns and the area. The percentage change in the voltage sensitivity will be, now what is voltage sensitivity? That will be theta by V, it is NAB by CR. So I'm assuming, so here the resistance is not changing. So if the resistance is not changing, C is also constant, N is also constant. So if the change in A and B is such that this factor increases by by 25%, so we can say voltage sensitivity should also increase by the same percentage. So option 1 should be the right answer. Now let us see this question. The current sensitivity of a galvanometer can be increased by, so current, this is theta by I, which is NAB divided by C. So by decreasing the number of turns. So if we decrease, it will decrease. So that is incorrect. We want to increase. Increasing the magnetic field. Yes, it is directly proportional to magnetic field. So B is correct. Decreasing the area. That is incorrect because it is directly proportional to area. Decreasing the torsional constant. So by decreasing C, the current sensitivity will increase. So D is fine. That is also correct. So B and D is the answer. So option D is the right answer. Let us see one more question. Moving coil galvanometer has 100 turns and each turn has an area of 2 square centimeter. This is N, this is A. The magnetic field produced by the magnet is 0.01 Tesla. So this is magnetic field and the deflection in the coil is 0.05 radians. So this is theta. When the current is 10 milliampere, so this is I, is passed through it. The torsional constant of the suspension wire is x into 10 raised per minus 5 Newton meter per radian, the value of x. So we know the formula, so that will be C theta is equals to NIAB. So we have to use this and we want to find the torsional constant. So this will be NIAB divided by theta. So let us put the values. So 100 times the current is 10 milliampere, so 10 raised per 10 raised per minus 3. Area is 2 into 10 raised per minus 4. Magnetic field is 0.01 divided by the angle or the deflection. That will be 0.05. Okay, let me remove this decimal. So we got 2. So it will be 4 times 10 raised per 2 minus 3 minus 4. So which comes out to be 4 into 10 raised per minus 5 Newton meter per radian. So so in this case x will be 4. Now the next concept is based on magnets. So if we have given a bar magnet, let us, this is the north pole and this is the south pole, and it is having a magnetic dipole moment m, then the magnetic field at a point on the axis or at the axial position will be given as 2 times mu naught m divided by r cube for short magnets, where r is the distance of this point from the center of the magnet. And if we have want to find the magnetic field at the equatorial position, in this case if the magnetic dipole moment is in the upward direction, it is always from south pole to the north pole, then the magnetic field will be opposite to that. So this magnetic field will be minus mu naught times m divided by there has to be a 4 pi term also in the denominator, right? So it will be 4 pi r cube. So this you have to remember. Now let's see some questions. The magnetic potential due to a magnetic dipole at a point on its axis situated at a distance 20 centimeter from its center is 1.5 into 10 raised to minus 5 Tesla meter. The magnetic moment of the dipole is. Okay, right. So let me also tell you the potential. So here we have discussed about the field. So potential at the axial position will be, so if you if you remember the potential due to the electric dipole, we can derive the formula for magnetic dipole. For example, in case of potential for dipole, the formula is K P P dot R divided by R cube, right? This is the formula, and we can write this as 1 upon 4 pi epsilon naught times P dot R divided by R cube. Now what you can do, instead of epsilon naught, you can replace this with 1 by mu naught, and you can replace electric dipole moment with the magnetic dipole moment. You will get the formula for um, magnetic potential. So that will be mu naught by 4 pi times m dot r divided by r cube, or we can write this as mu naught upon 4 pi m m by r square cos theta. Now in case of a axial position, theta will be 0 and cos 0 will be 1. So the formula is mu naught m upon 4 pi r square. Now here the magnetic potential due to the magnetic dipole on the axis, so we can say mu naught by 4 pi m by r square. This is given as 1.5 into 10 raised per minus 5, and the distance is 20. So I'm assuming that the magnet is short, so that this formula is applicable for short magnets. So it will be 4 pi into 10 raised per minus 7 divided by 4 pi, and we have to find m, and r is given as 0.2, so square of that, so 1.5 into 10 raised per minus 5. So 4 pi will get cancelled out. So magnetic dipole moment will be 1.5 times 4 times 10 raised per minus 2 minus 5 plus 7. So this comes out to be 6 ampere meter square. So 6 is the answer of this question. Right, so a straight magnetic strip has a magnetic moment 44. So we have given a straight strip. Let us say this is the north pole and this is the south pole, and let's say the length between them is L, and the pole strength is M. This will be minus M. So we can say magnetic dipole moment will be M times L, and it is given as 44 ampere meter square. If the strip is bent in a semicircular shape, its magnetic moment will be, so if we bend this into a circular shape, then we can say let us say r is the radius, then pi r will be equals to L, right? So r will be L by pi. Now this is M, this is minus M, so the new magnetic dipole moment will be M times 2r. So it will be M times 2 and r will be L upon pi. So let us put the value. So M times L is 44. So this will be 2 by pi times 44, and pi value is given as 22 by 7. So it will be 2 divided by 22 times 7 times 44. So this will give us 2. So it comes out to be 4 times 7, 28 ampere meter square. So answer is 28. Now the next concept is based on magnetic materials. So again, the link for magnetic material I have shared in the description. You can watch the theory part from there. So let us see the question. Given below are two statements. Statement 1 is for diamagnetic material, the magnetic susceptibility is negative. It lies between -1 to 0. So that is fine. So option statement 1 is correct. Statement 2, the diamagnetic substances when placed in an external magnetic field tend to move from a stronger to weaker. Statement 2 is also correct. So both the statements are true. So option 2 is the right answer. Permanent magnet substances, so we have given A, align themselves along paramagnets. So paramagnetic substances align themselves along the direction of the external magnetic field, attract strongly towards the external magnetic field. So they attracted weakly, not strongly. Has a susceptibility little more than the 0, so that is fine. They have a susceptibility which is positive and very small. It is having a very small value. Move from a region of strong magnetic field to a region of weak magnetic field. So this is wrong. They move from a weak magnetic field to a strong magnetic field. So C is fine. C is correct. D is incorrect. So we can use elimination. 2 is incorrect, and B is also incorrect. B is also incorrect. So align themselves along the direction of the external magnetic field? Yes. So option A is also fine. So option 3 is the right answer. If you find videos of this series useful, so it is highly recommended for you to join PracBee's revision program. So in this program, we're going to cover 10 blocks in 10 weeks, and we'll give you a target of 1 chapter per day, and we'll be able to cover all relevant chapters by the first attempt of JEE Mains. And how you can join this revision program? By clicking on the link given in the description. And one more thing you can do, please drop a comment. Let us know what else we can do for you to make this series better. Thank you.